All right, so trigonometry, this is page 7 in your packet, and then if you slide to the bottom of it, I want to talk about these a little bit more. Do you know that this is the general form for all of these things? With A, B, C, and D. Let's talk about those. The number in the front, that's called, it starts with an A, and it is an A. Do you remember what that's called? Amplitude. Very good. I see a couple people with headphones in. It's a good time to take those out. Give me your full attention. All right, here we go. So A is amplitude. B, I betcha, I guarantee ya, you're going to be asked a question about B on the test, because there's this really important thing about the period and B. Do you remember that little formula that has period and B in it? If you don't, you're about to get one wrong in the final. So, anybody remember that one? Yes? Go ahead. All right, so 2 pi over B is definitely key. What is 2 pi over B? The period. That is a key one. You better write that one down. I would put it right down in that neighborhood. There's more questions coming about that. They're going to say, what's the period of this function? All right, so let's look at this one, for example. What's the period of this function? Well, the period is 2 pi over B. If I only knew what B was. There's no number in front. Yes, there is. What's the number that's in front? 1/2. Would you agree that theta over 2 is the exact same thing as 1/2 theta? So there is a B term here, and the B is a half. So do you get, if I put a 1/2 here, dividing by a half is the same as timesing by 2? Does that ring a bell? So this would be, period is 2 pi divided by a half. That's like 2 pi times 2. You do the opposite of what you'd expect on the inside. All these math rules I've given you kind of come together. You would think this would cut it in half. It doesn't. It doubles it. Final answer, 4 pi. That's the period of this function. Now, I know in this question they might not have even asked you that, but they are going to later ask you about period. So that is a key equation. Okay. Next thing, if you look at this, for example, that's on the outside and that's on the outside. Would you please circle these and put vo? What the heck does that mean? Vertical on outside. Okay. Then, there's nothing on the inside, but if there was, it would be a high. Horizontal changes are on the inside. And remember, on the stuff on the inside, it's the opposite of what you would think. Like, you would think that this makes it 4 times horizontally. But it's the opposite of that. It's 1/4 as big horizontally. Remember that deal? Opposite of what you would expect on the inside. All right. Do you remember that these are called, I would call them a flip, but you know that isn't really a math word, right? What's the official name for a flip? Reflect. Very good. So that's a reflect. And what if you're multiplying by something, but you're multiplying with something really small? Is it still a stretch? No. This would be a shrink. And it's a vo, so it's a vertical shrink. It's on the outside. This one was on the inside. That's a horizontal change. High vo. All right, so that's what's critical in problem 15. Let's move on, everybody. Go to page 16 of the packet. And if I had to graph trig, I'd have to know some trig. I have to know what sine, cosine, and tangent look like to be able to graph these. Like, I'm not even going to graph secant. I'm going to graph the sister of secant. And that brings up something we haven't even talked about, which is, which one does secant go with? All right, so up at the top, please put sine. And we're not going to say equals because it's not equal to, but sine goes with what? Cosecant. They're sister functions. So really, sine is equal to 1 over cosecant. But I'm just saying those go together. Cosine. Do you remember what that one goes with? secant is correct. And the last one is tangent. Its sister function, its reciprocal is cotangent. Good. So remember, again, if you wanted to say equals in there, you'd have to put 1 over. All right. So if I told you sine was a half, cosecant would be 2 over 1. You get what I mean? And then how would I get cosine? I'd have to go draw my picture. And I'd have to go sine gave me opposite and hypotenuse. 1 and 2. Oh yeah, 1, 2 square root of 3. And then from there I could know all my angles. Cosine would be root 3 over 2. And then secant would be the flip of that. And tangent would be TOA, opposite over adjacent. And the flip of that. And I gotta flip this one now. So those are the 6 functions. I'm gonna be like fire hose of information here, but every single thing I'm telling you is on the final. So it's worth writing down, which jogs your memory, which improves chances you'll remember it on the final. Plus, you might not care as much right this second. You might feel burned out. But right before the final, if you can look over your packet and in the margins you have really critical notes like you're taking right now, you'll thank yourself later because right before the math final, you'll have something to go back and look at. And like, oh yeah, these are important. Which one goes with which one? Okay. Next, let's go off to the margin here and just make a graph of normal sine. I know it's been a while. You're going to for sure need to graph normal sine. And it looks like that. It goes from 0 to 2 pi. It goes up as high as 1 and down as low as -1. And then you had to know the little spots along the way. I like to think of this as, well, half of this would be 2 pi would be pi. And then half of that, again, will be 1 pi over 2 or pi over 2. And then I like to count it up and say this is 1 pi over 2, 2 pi over 2. This is 3 pi over 2, and this is 4 pi over 2. And in graphing was the only time I said you could leave things unreduced. Because I see why you'd want to call that 4 pi over 2. So that if you had to go to the next mark, you would know the next mark over would be 5 pi over 2, etc. Okay, so counting by pi over 2 is really smart. All right, so there's my graph of sine. Do you guys remember sine? All right. Now, if you want to save yourself time, and I do, I'm going to put sine right on this, and then I'm going to put cosine on the same graph. You may want to put cosine on a different graph, but I'm going to try to get it on the same graph. This cosine ends at the exact same spot, but it's like this red line. It's like a big valley. It starts high, it ends high. Also has a period of 2 pi. Okay. And then there's tangent, which is a different one. And cotangent is like related to tangent, and that's even more different. So I'm going to make another graph down here for tangent. And tangent goes like this. If you know the base tangent graph, you can do any of the stretches, etc. Yes?
Is like finding the amplitude and period the same for tangent?
Good question. Tangent doesn't have an amplitude. It's weird, but the number in front of it isn't an amplitude because amplitude is like how high the thing goes, and this thing goes up forever. So tangent doesn't have an amplitude. And tangent doesn't have a 2 pi period. Let's talk about that. I'm just about to put these on here. Pi over 2 and negative pi over 2. There's your tangent graph reminder. I would sketch that if I were you. Now let's talk about it a little deeper. I was just asked about the period of tangent. Well, the period of tangent is how long it takes to get a complete cycle done. Well, this distance here is pi over 2, or half of a pi, and this is another half of a pi. That means its period is pi. So that little formula that I gave you before, that only works for sine and cosine and the sister functions for it. So here's the formula if you're doing tangent. Pi over b. Why not 2 pi over b? Because the period of tangent is just pi. May want to write that one down. Okay, then I'm going to make cotangent's general graph, because then stretching it and moving it is fairly easy. But here's cotangent. And again, I don't have time to explain where it all came from. I taught you that before. I have time to quick remind you what it looks like. And this is pi. Because it goes from 0 to pi, it also has a period of pi, but it's kind of shifted over from where the other one was. It's flipped over and shifted over. All right, so that's cotangent. And then last but not least, we got to do the sister functions, which are secant. See, they're asking us to graph secant here. And you probably want to know what secant looks like. Here's secant. Do you remember that you don't actually start with secant? You start with the sister of secant, which is cosine. So here I am graphing cosine again. Better know cosine or you won't know secant. And then I go and say, since secant is really the flip of this, as in the inverse of this, then wherever this thing hits 0, you had to have 1 over 0, so it doesn't exist. So there's asymptotes here, and it goes like this. Thankfully, this year we backed off on making you have exactly 1 period of it. Because see, this technically has 2 up loops and 1 down loop. And we used to mark wrong for that because, you know, you're supposed to have equal numbers of them. But kids would forget all the time that they technically should, if they only wanted 1 period, you should chop off this and this. But if you're allowed to give more than 1 period, which you will be, then that thing can continue and you can have infinite upper loops and infinite lower loops if you can graph more than just 1 period of it. Okay, so there's secant riding on the back of cosine. And the actual cosine graph, just to be really, really clear, you really ought to erase it. And I don't know if this will be a multiple choice question and therefore you won't probably make that mistake, but that's what secant looks like. It rides on the back of its sister. Now, how about the last one, cosecant? Remember, we had a whole chapter on these graphs. They're for sure going to be on it. And cosecant is fine as long as you know its sister, which is sine. There's sine. And it's same deal where it's 0, 1 over it won't exist. So there's asymptotes running down like this. And then the loops go like this and this. So if you know what original sine looks like, you really know sine and cosecant. Okay, there's the big graphs. Now, what if I put a 2 in front of this whole thing? Well, then you got to stretch the original graph twice as high as it used to be and twice as low as it used to be if there was a 2 there. I'm not putting a 2 there, but if I did, that's what you'd do. Or if I put a negative in front, it would have to flip over the graph. If I put a -3 here, the whole graph, everything about the graph would move down 3 if there was a -3 out there. Now, what about the most complicated kind? That is where you shift it to the right. See this thing right here? You'd graph your normal sine graph, and then you have to move everything to the right pi over 2. So the way I do it is I graph my normal sine graph, for example, and then I make sure I know where pi over 2 is. That's how far over pi over 2 is. And this is pi, and wait a minute, 1, 2, 3, 1, 2, 3. Oh, I missed. I needed to go 4 marks over. There. It looks a little off, but it's actually right. 3 pi over 2 is right here, and this is 2 pi, or 4 pi over 2. Okay, now, if I want to do this, I want to shift it to the right pi over 2. How far is pi over 2? It's that far. So everything moves over 2 marks. This moves over 2 marks. This moves over 2 marks. This moves over 2 marks. Everything moves over 2 marks. You can finish it from there. I think you get the idea. All right, and they don't even have you practice anywhere. Oh wait, here's one. There's a 1/3 in here. You would multiply all your x numbers by 3. You know, the opposite of what you think. You'd multiply all your x labels, all these numbers that you label here and here and here and here. You'd multiply them all by 3, not 1/3, but 3. To do that kind of stretch. Okay, man, tough to review everything. This is just more of the same, so we're going to go to number 17 now. This is the all 6 trigonometric functions, but I needed to remind you about they were because we were graphing secant, so I already did this part. And for example, here, if I had to answer this question, I would go sine, cosine, tangent, and then I'd do the sisters right next door. Cosecant, secant, and cotangent. And then I'd figure out which one they gave me. Okay, they gave me cosine's 5/11ths, so that goes right here. And that automatically tells me secant is 11/5. You know, you just flip it. But then you might be like, well, how am I supposed to do sine? Well, you take the 5 and the 11, and you go, well, I guess they've given me a triangle where cosine is adjacent and hypotenuse. They've given me everything I need. This third side, oh my gosh, another thing I taught you, finding the third side of a right triangle the fast way. We go 11 squared is 121. And is this the longest side? Because if it is, I would add them. But no, it's not. So then I go minus. And then 5 squared is 25. That's how you get that third side. Okay. Now that I've got that, it's the square root of 96, I'm pretty sure. I'm going to double check that. 111. Nope. 86. Nope. 106. Nope. Dang it. Was it 96? 100, 110, 121. Yep, it was 96. Thank you. Okay, so then my third side, wherever I need it, for like sine, which is opposite over hypotenuse, is square root of 96. So square root of 96 over 11. And then you flip it to get cosecant, etc. That's how you do that one. Here's the 6 functions: sine, cosine, tangent, and then the sisters go over here. And then this one tells you the sides by telling you a triangle with the sides. And then this last side you'll do square root of, and you'll figure it out that way. Okay, then we talked about these yesterday. Yay. So if I asked you for cotangent of pi over 4, you wouldn't do it. You'd go do the sister of it, which would be tangent of pi over 4. So I'd really think of this as, hey, I refuse to do cotangent. I'm doing tangent of pi over 4. Can you flip the angle? No, but whatever you get for your answer, you flip it. Because we just flipped the function. You know what I mean? We're not doing cotangent, we're doing tangent. So how do I do tangent of pi over 4? Well, I draw it. Pi over 4 is a 45-degree angle. 1 root 2, because I know the 45, 90. And then I'm doing tangent of that. Oh, TOA, opposite over adjacent. 1 over 1 is 1. And then I flip it. When you flip 1, you still have 1, don't you? So there's your answer. So remember, if you're doing the weird ones like secant, don't do secant. Do the sister, which would be cosine. and I do cosine of 4 pi over 3. But it's not exactly the same as that, so you remember you flip cosine of 4 pi over 3. So 4 pi over 3, here's 3 pi over 3. 4 pi over 3 is like there-ish. Draw my triangle. That's a 60. I know that one. 1, 2, square root of 3. Don't forget the most common mistake in circle trig, negatives. There's your little drawing for letter H. And once you've found the cosine of it, remember you're going to want to flip it at the end. I wish I could spend more time on these, but to have any chance of finishing, I have to run through this. Okay, so, and I really want to finish it because the seniors have to take the test starting tomorrow. So I'm trying to give them their last chance at taking this and really, studying it well. There are answers, of course. There's a key for all of this. So this is a certain kind of trig when we hit number 22. It's called the circle trig? No, they've all been circle trig up to here. They're called, starts with an I, inverse trig. Very good. And whether they say arc or have a little power of -1, it means the same thing. I told you on these to always start by rewriting it like this. I said it was like sine of some angle is √3 over 2, but it's like that, but there's only certain places that inverse sine can live. So strong recommend that right now you write down this diagram. This is where inverse sine can live. So do you get I'm restricted? I can only be in quadrants 1 and 4. And since sine is positive, see there's no negative here. Sine is positive and I can only be in these two spots. Well, that narrows it down to only one spot. Know what I mean? So some things I told you about inverse trig that were different. They can only live in certain places. And let me finish that thought. This is where, do you remember which one goes there to there? Cosine, very good. And then tangent is exactly the same as sine, false. It's really close. Except it doesn't touch the edges because tangent has asymptotes on the edges of it. So this is inverse tan. Now, if you're starting to feel hopeless, like I can't remember all this stuff, remember if you can get a 75% on the easies and the hards, you're going to get an A. So I understand there's going to be a few you don't remember, but really try hard to remember as much as you can. And you don't have to remember it unless you're a senior. You don't have to remember it tomorrow. But you should come up and ask me questions when you get stuck. All right, so this is a really critical drawing, and there was two more parts to this that get people all the time. This here is called the negative zone. Because anytime you're in there, you have to give your answer as a negative angle. Inverse trig is weird that way. Because this is not 3 pi over 2. This is negative pi over 2 in inverse trig. I know, it's hard to remember everything, isn't it? And notice there's nothing in here. This is the dead zone. None of the trig functions work. The inverse trig, just clarify, none of the inverse trig functions work out there. All right, so remember me saying you start it, it's like a regular circle trig question, but it's not allowed in certain places. So this was inverse sine, so I know it's only allowed from here to here. So I'm crossing off this and crossing off this. Now, since sine is positive, it only can be here. And notice I said inverse trig questions only ever have one answer. Regular circle trig questions usually have two answers or infinite answers. Inverse trig, only one answer. Okay. So now, sine is opposite over hypotenuse. And this must be the 1, 2 square root of 3. What's across from the 1 is a 30. What's across from the root 3 is a 60. but I can't say 60 because it's in radians. Do you have memorized yet? Pi over 3 is correct. That's what 60 is. So this but here is reminding you, you can only be in those two quadrants because it's inverse trig. There's the key for inverse trig. Totally get, you're gonna need to practice that. That's why you got a whole bunch of problems and a key. All right, and if you get stuck, come up and ask me. All right, moving on to page 12. Can you believe we've made it to page 12? All right. Man, part B, I'm stuck. I don't know what to do. If the whole class is stuck on something, what has the answer been usually? Factoring. If you get just brutally stuck in logs, it's usually rewriting. Here, it's usually factoring. If you're just like, I'm lost, it's probably because you didn't notice it factors. Do you get there's a cosine in both of them? You factor it out. Cosine is now on the outside. And what would be left on the inside? 2 cosine plus 1. Is that just the answer then? No. Now you got to set this equal to 0 and this equal to 0. And then you can solve it from there. Now, one thing you may have noticed is pretty much absent is, do you remember that one test we had on like sine squared plus cosine squared equals 1? And you had a partner as the only partner test pretty much all year. Okay, that test, I'm not promising nothing on it, but if I was only going to remember one thing from that test, it is that sine squared plus cosine squared equals 1. Because, oh, and one other thing, like tangent is sine over cosine. We're not going to ask you for the really complicated ones because I'm pretty sure we're not giving you a sheet. If we don't give you the sheet, you're never going to remember what cosine of 2 theta is. I don't even remember what cosine of 2 theta is. I got to look it up. But these two, and the things that kind of come from them, you should know because they're also can be on the ACT, and they also can be on your in calculus. Trig is going to come back. All right. This can be factored. This can be factored. You might not feel like this can be factored, but maybe it's because you didn't realize there was a cotangent in both of them. You know, just factor it out. All right, we have covered everything. A senior, in theory, could nail this final tomorrow. You'd have to study really hard tonight. The rest of you guys that aren't seniors, lucky you. You got more days to ask me questions. Finish up your packet. I know you don't have to do them all. And you don't even have to do them all tonight. Just do a little bit tonight. Unless you're a senior, in which case you should finish about half of the packet by tomorrow. That's all I got for you for today.